Wondering what they hoped to learn at NOvA was natural curiosity. But an even more basic question is how the research idea came about in the first place.
How this really started off is back in the early 80s with almost no funding at all. The University of Minnesota and several universities from England built a very small 35-ton detector looking for proton decay. That was the big thing back then. People weren't even worrying about neutrinos at all. And so we got funding in the mid-80s to build a large detector. This is when I started in 1984 to build a large proton decay experiment. In fact, you can see here when I had quite a bit more hair and was a little skinnier. And this proton decay detector never did see any protons decay. But what we did see is that we didn't understand anything about neutrinos. We knew that we would see atmospheric neutrinos in this detector, and in fact we were worried about it being our background for proton decay because they look very similar. So a proton decay, you would expect all of the energy to deposit in equal directions. So if you added up the vectors of the particles, they would all equal zero when you added them all up together. Where a neutrino comes in and you don't see the neutrino, and then you see two legs of your signature event coming out. And so we were worried that that would fake us out. But it turned out that we weren't seeing the right ratio of muon neutrinos and electron neutrinos. And so this experiment, the experiment in the salt mine in Cleveland, there was a big Shrankoff water detector. We all were seeing the same thing, saying the theorists have to be wrong. We're seeing a totally different picture here. And so then all of a sudden, the new big buzz thing in physics was for the only way for this to happen is neutrinos must have mass. Before this, everybody thought neutrinos didn't have mass. And so that was when we built the large MINOS detector at Sedan. When we were talking before, I told you it was a big toroid magnet because it's made with plates of 1-inch steel and 1 centimeter of scintillating elements. And this scintillator was plastic, but it works essentially exactly the same as the liquid scintillator. And then we moved to the NOvA detector, and this is the scale of how big the detector looks if you put it inside the Metrodome. It just about fills it from one end to the other.
By the way, although shooting on this film began about a month before demolition started on the Metrodome, we still use it for scale reference in this film. Case in point, this image shows what the NOvA detector would look like inside the Metrodome. But a question comes immediately to mind. Just who would have need for such a massive detector? That's easy. Researchers at a university, of course.
This facility was built by the University of Minnesota and managed by the University of Minnesota, but the funding all comes from the Department of Energy, and of course Fermilab, which supplies our neutrinos from the neutrino beam, is also highly involved. So it's kind of a three-ring circus almost.
But they built the NOvA facility in a very remote location.
Why was it important to build NOvA as far away as possible?
So the neutrinos, when we launch them from Fermilab, they're traveling very nearly the speed of light. So they only take a few thousandths of a second to get all the way up to northern Minnesota. It's a lot longer on United, let me tell you. And even worse if you're driving down 53. But the neutrinos, as they travel, have a little bit of time in which to change. The further away you go, that much more time for them to change. Now, of course, you could also just dial down their energy and make them travel more slowly, and you get more time to change too. But the lower energy the neutrino, the less well they interact with your detector, and they're already so darn slippery that the more we can jack up the energy, the better chance we have to see them, and the better chance they have of making a good splash so that we see what's going on. But to get that energy and make that as obvious as possible, you have to go as far away as you can.
A question in my mind was, why did they want to build NOvA off-axis from the main neutrino beam between Fermilab and Sedan?
Yeah, the beam itself is aimed and focused right at the Sedan Mine underground lab, where the first experiment using this beam, MINOS, lives. And for that experiment, we knew far less about how neutrinos behaved when we started that 10, 15 years ago. than we do now. So we wanted all the neutrinos we could get. So the beam was focused and aimed right there and intense. And to make it intense, you take all the neutrinos you make at Fermilab and you get to try to focus and aim them right there. So you get a lot more neutrinos. But you get all the neutrinos of all the different sorts and speeds and energies and everything else. And so it's messier to sort out what's going on. You don't know which neutrino, the neutrino that made the splash in your detector, was it of this energy or another energy, because you have them all. But if you go off to the side, you're missing most of the neutrinos, so that's bad. But the ones that do end up aimed just at that particular angle off axis are all of about the same energy. When we see one, we're pretty sure when we see the splash it made, we know a lot about the neutrino that made it, instead of it could be any one of this whole zoo of them. And so we're able to be more precise.
But one wonders, why was NOvA built specifically at Ash River?
We knew we wanted to be about 14 kilometers off the center of the beam, and so we just drew a straight line, and we picked someplace high in a hill because we didn't want to build in a swamp.
This is kind of an overview map showing you that the center of the beam line is aimed right at the Neutrinos detector at the bottom of the Sedan Underground Lab, and we want to be off axis, and so we knew we wanted to be about 14 kilometers off the axis of the detector, and we wanted to be as far away as we possibly could from Fermilab, and so this was the last east-west road in the United States. We actually looked quite hard at building the detector up here in Mine Center in Canada, but it just wasn't very feasible. There wasn't enough power, there wasn't any fiber optic there. It would have just been way too costly for the little bit of distance that we would have gained in length. And so in the end, we worked with the state of Minnesota and got the property from the DNR.
When I asked when they got the go-ahead to start constructing the NOvA facility, I learned that it wasn't as simple as, here's the money, go ahead and start digging.
Before you get $280 million for funding a large project like this, you have to start at the very beginning and convince DOE and the Department of Science and Engineering that they really want to fund this project. So you have to prove that the physics is there and that you're capable of actually building this detector. And so we were working on it roughly about 12 years from when we first started the original design phase before we actually started building the detector. And then the last few years before we started was building the building. And this building costs roughly $40 million, including building the road into the site because we're in the middle of nowhere here. There was no road. And putting in power and fiber optic lines and all of those things would be included in the infrastructure for the building.
And I made about 3 dozen trips into here where you had to walk all the way in from the Ash River Road to select the site and make sure we were doing it in the right place. We had to do all sorts of core drilling and things like that. And then we finally started building on the site. So I was here at least once a week all the time during the civil construction just to monitor things for the university as they drilled and blasted their way down.
Construction of the NOvA facility started in the summer of 2009. 56,000 cubic yards of granite had to be blasted out. The resulting rectangular cradle of bedrock would help screen out other types of particle rays that make up, so to speak, a background noise. An on-site crusher recycled much of the blast rock for uses such as roadway aggregate. And an on-site batch plant produced 16,000 cubic yards of concrete. The resulting concrete walls now serve as secondary containment for the neutrino detector's oil-filled modules. And the technology behind the detector is cutting edge. In fact, they had to challenge the industry to come up with a way to make the key component, the detector modules.
The modules they're made out of extruded PVC. They're made by a company named Extratech in Wisconsin. And that's one of the questions that people ask, what does all of this science do for us? And that's one of the little small offshoots. When we first went to the extruders, they said, "Are you guys crazy? Nobody's ever extruded anything that big, that flat." And it took many years of playing around with the chemists and scientists and engineers to come up with the right die to actually make it. And now Extra Tech can use that technology for extruding garage doors or other items that they could never make quite so accurately.
The NOvA project has really lifted Extra Tech to the next level, I believe. It's brought extra expertise into the company that we've hired people from the outside to assist us in both quality control and in the actual process of the panel.
Once the plastic tubes had been fabricated, they were shipped to the University of Minnesota, where they were made into the modules.
Down at the University of Minnesota, they make them into modules, and they do that by putting an end cap on 2 extrusions, and then they put long, actually every module uses a full kilometer of green wavelength shifting fiber in each module, and then they seal it on the top with a manifold that allows us to hook the electronics to it to read out the signal. And so all that work gets done at the University of Minnesota, and once they've passed all the tests, then they ship them up to us. And typically we get 6 or 7 module shipments per week. That's roughly how many modules. We put about 175 to 200 modules in the detector every week with the crew.
And how many modules will you have when the project is completed?
Oh, you asked me a tough question. So it's a little over 10,000. There's 384 modules in each block, and we're building 28 blocks.
Okay.
So we're actually, right now, we're working on the 25th block, and that will go in place in just after Thanksgiving sometime.